Hello, everyone. I am Xietao, from Harbin Institute of Technology. Today I will introduce our work OFVL-MS, once for visual localization across multiple indoor scenes. OFVL-MS is a unified framework that dispenses with the traditional practice of training a model for each individual scene and relieves gradient conflict induced by optimizing multiple scenes collectively, enabling efficient storage yet precise visual localization for all scenes. Technically, in the forward pass of OFVL-MS, we design a layer adaptive sharing policy with a learnable score for each layer to automatically determine whether the layer is shared or not. Such sharing policy empowers us to acquire task-shared parameters for a reduction of storage cost and task-specific parameters for learning scene-related features to alleviate gradient conflict. In the backward pass of OFVL-MS, we introduce a gradient normalization algorithm that homogenizes the gradient magnitude of the task-shared parameters so that all tasks converge at the same pace. Furthermore, a sparse penalty loss is applied on the learnable scores to facilitate parameter sharing for all tasks without performance degradation. Visual localization aims to estimate the rigid transformation of a given RGB image from camera coordinate system to world coordinate system. Contemporary cutting-edge learning-based approaches for visual localization could be categorized as absolute pose regression, relative pose regression, and scene coordinates regression. Thereinto, score methods directly predict scene coordinates by using a trained convolutional neural network, accompanied by a perspective endpoint algorithm to retrieve the camera pose. While these methods deliver impressive results, they encounter some flaws. Scene coordinate regression is scene-specific and required to be trained for new scenes, resulting a linear increase in total model size with the number of scenes. Multitask learning can provide a solution to address this challenge, where each scene's localization is treated as an individual task. Nonetheless, two issues merit further investigation. First, how to identify which parameters should be shared or not among scenes for profitable and efficient localization of multiple scenes. Second, we exploit to perform visual localization with multiple dataset domains as input rather than one dataset domain used in regular multitask settings. Therefore, under such setting, MTL would culminate in significant discrepancies in the gradient magnitude of various tasks. Towards this end, we propose OFVL-MS, a unified visual localization framework that optimizes localization tasks of different scenes collectively in a multitask learning manner. OFVL-MS consists of layer adaptive sharing policy and a gradient normalization algorithm. We designed three versions OFVL-MS 18, OFVL-MS 34 and OFVL-MS 50 by using ResNet 18, ResNet 34, ResNet 50 as backbone respectively, and then compare OFVL-MS families with other state-of-the-arts on 7 scenes and 12 scenes datasets. As shown in the tables, OFVL-MS 50 yields 0.021 m median position error, 0.69 degree median rotational error and 88.72% 5 cm 5 degree accuracy, establishing a new state-of-the-art for 7 scenes dataset. On 12 scenes dataset, OFVL-MS families exhibit exceptional performances, in which OFVL-MS 34 realizes the most superior performance with the positional errors of 7 mm and localization accuracy of 99.9%. We compare the storage space occupied by different methods to demonstrate the efficient storage deployment of OFVL-MS families. OFVL-MS deposits multiple models with a majority of shared parameters into a single one, realizing efficient storage. OFVL-MS families reduce the model parameters significantly compared with other state-of-the-arts. For 7 scenes dataset, the parameter size of OFVL-MS 50 is only 1/5 of that of HSCNet, but the localization accuracy is improved by 3.92%. For 12 scenes dataset, OFVL-MS 34 achieves the best performance with much fewer parameters. We also visualized the cumulative pose error distribution, point cloud, camera trajectories, and predicted uncertainty in the figures. We conduct 2 experiments to demonstrate that OFVL-MS can generalize to new scenes with much fewer parameters and thus can scale up gracefully with the number of scenes. We utilize the model trained on 12 scenes and conduct the generalization experiments on 7 scenes. Despite generalizing to a new scene, OFVL-MS 34/50 still outperform HSCNet and FDANet by large margins. The same phenomenon can be also observed in the generalization experiments from 7 scenes to 12 scenes. We also introduced the challenging LIVL dataset containing RGBD images tagged with 6 2F camera poses collected around 4 scenes. First, K544, spanning about 12 by 9 square meters. Second, Floor 5, spanning about 12 by 5 square meters. Third, Parking Lot 1 spanning about 8 by 6 square meters. Fourth, Parking Lot 2 spanning about 8 by 8 square meters. Each scene contains 3 sequences for training and 1 sequence for test. A massive proportion of motion blur and sparse texture in the scene make visual localization in the 4 scenes challenging. The dataset was collected using an autonomous platform armed with a RealSense D435 camera and a VLP-16 laser radar. The RGB and depth images are captured at a resolution of 640 by 480 pixels and aligned with point clouds using timestamp. We utilize the LiDAR-based SLAM system alone to compute the ground truth pose. Compared with typical score-based methods SCORDNet and FDANet, OFVL-MS families outperform them by non-trivial margins in terms of all evaluation metrics while necessitating much fewer total parameters.